Hi, welcome to this video in the MicroTasker Shorts series. Today we're going to be looking at the FRDM-K22F board and in particular at low power cycle option which is available in the MicroTasker code. We start with a discussion of the lower power support in the MicroTasker project. At the top here we see the MicroTasker scheduler, which is responsible for coordinating a number of tasks in the system. The task of interest here is the low power task itself. This task is responsible for putting the processor into a low power sleep mode, let's call it, whenever there is no system activity. The way that it does this is by disabling interrupts and then commanding the sleep mode. Exit from the sleep mode is via certain interrupts or other wake up events in the system which can achieve the wake up. The normal method would be that we would enable interrupts again. Whatever interrupt caused the exit from sleep would then be handled immediately because it is pending, and the lower power task will then pass back control to the MicroTasker scheduler, which will then allow tasks to operate based on the events which are now pending. Eventually, the low power task will then allow the processor to go back to the sleep mode. What I would, however, like to discuss is this part here, which is called the virtual wake up interrupt handler. Now, when I enable the virtual wake up interrupt handler operation by setting the system to low power cycle enabled, then we don't recover by the normal process. What happens is immediately after the exiting the sleep mode, we call the virtual wake up interrupt handler, which will look to see why we woke up, do some work if it wants to, and then go immediately back to sleep. The advantage of this operation is that we do not need to re-enable interrupts and take the context switch. We can remain in this tight loop and we can spend more time in the actual sleep mode. We will see this later in a practical demonstration. However, the virtual wake up interrupt handler has also the option at any point in time of passing back the control so that the normal scheduling can take place. What we see here is a cam of the board in operation. We can see that we have an LED which is blinking. The basic setup is that we have a system tick of 250 microseconds. That means 4,000 times a second we will have a wake up interrupt. The board is also connected to a terminal emulator where I have the possibility to command the low power operation. If you look at the cam at the moment, we see that normally we have 3.1 milliampere of current consumption. The processor is not running particularly quickly, it's only set up to run at a core clock rate of 4 megahertz. In the administration menu I can check the low power modes available. Now what I'm going to do now is I'm going to change into the very low power stop mode and we'll see what happens. The stop mode is number 4. We see that we didn't actually get a lot of change in the current there. We're going to have a look at to see why that is. Using a logic analyzer we'll take a look at the operation. Here we see the blinking LED which has a period of every 200 milliseconds. If I zoom in now, we can look at what's taking place in the low power part of the operation. What we see here is a cycle. The cycle is repeating at about 250 microseconds. So this is our basic operation. This point here is when we wake up out of the low power mode. This is the handling routine, and at some point in time we go back to the low power mode again. So what we see is that the amount of work required by the scheduling to wake up, to do its work, to go back to the sleep mode is taking up almost half of the cycle period. Now the effect on the current consumption is that we are running at full power here and we are only making full use of the low power here. Now I'm going to command the low power cycling mode and we're going to watch what happens to the current. Here the current is now reduced, and we're going to look at the screenshot again. Let's take another recording. We see that basically everything is operating as before, but if we zoom in now, we're going to see a difference. Again, we see our cycle. Here's a cycle period, 250 microseconds more or less. And the difference is now that we're moving between the sleep mode. We're executing the virtual wake-up handler to do our work rather than letting the work be done in the pending interrupt itself, and then we're going immediately back to the sleep mode. The effect is that we save the interrupt context switch, and we can effectively get back into our low power mode, which is represented now by not only 40% of the period, but let's say 75 to 80%, and of course the effect is that we get a good saving in the power consumption. At the system performance level, we don't actually notice any difference. I'll show you now why that is. Here I have the software which is actually responsible for handling the virtual wake up. What it does is looks to see whether we have any pending UART interrupts. It also looks to see whether we have any pending real-time clock, because I actually have a real-time clock operating, which I also don't want to lose the functionality of. In any of these cases, it will say we want to pause, and it will return so that we don't stay in this loop. That means that it decides we want to let the scheduler operate for a short amount of time to do the work which needs to be done because of this interrupt. So it allows the low power cycle loop to quit, it allows scheduling to take place, and this automatically returns and goes back to the low power cycling mode. In addition, what I do have to do is I have to clear pending interrupts because I don't have my interrupt routine anymore. I'm doing a small application here of retriggering the watchdog every 0.2 seconds, exactly as the system was doing in its full-blown mode. And I'm setting a couple of LEDs so that we could look at this behavior on the scope. Many thanks for watching. I hope you enjoyed this video. If there are any questions, please ask them. If you're interested in improving the performance of your lower power system, do take a look at uTasker.